Alright, good morning. In the last session we have started exponential function sections 4.2 and we were pretty much done except one application question. Why don't we review what we did last time quickly from the slides. Again, exponential functions shows up pretty much everything in growing and decaying can be modeled by exponential functions, such as this puzzle question that your salary is doubled every day. Would you be making more money than $1 million if you start with 2 cents at the end of the month or not? And we have investigated and seen that you're a lot ahead if you just accept 2 cents initial salary. You will be making a lot more. That's the power of exponential growth. And exponential functions, basically you have a number on the base and varying exponent. X is on the exponent. It's mostly confused by x squared. This is also varying a lot. I mean, it's growing a lot, but x is on the base and the number on the top. We call this a power function, not exponential. You need to have the number and variable flipped, like 3 to the x, to call it exponential. Again, we do not like to have a negative number in the base. No -4 allowed. No 0, neither 1 allowed, because 1 to the x is equal to 1. There is no exponent. We don't technically call it exponential. We have sketched them, and we notice that you either a growing graph, a rising graph to the right side, or sliding graph to the right side. This is decay, depending on the number on the base. If the number is more than 1, it's growing. If the number is less than 1, it's decaying. And we sketched a transformation graph, and we have learned about the number e. It's 2.7 roughly, and we have learned its graph. It's a growing graph because 2.7 is more than 1. And we sketched the transformation of e to the x. We did an example of an interest problem. This is most widely used application of exponential functions. This was our main formula, widely used one. But in case you are wondering, continuous compounding, PE to the RT is the formula for continuous compounding. If other periods like month, year, semi-annual, quarterly, then we use the second one. Alright, we were about to solve this question. This question uses continuous change, so it's not going to be about interest problem like this. It's more like PE to the RT, but they have already provided us with the formula, so you don't have to go with your own formula. So somebody modeled how this radioactive element, polonium-210, its the name is this, and this is the symbol, its symbol in chemistry. And this element is known to have a half-life of 130 years, 38 years, almost 138 years of half-life period. What does half-life means? It means if you have 1 pound of material right on this desk, and if you wait 130 years, 138 years, and measure again, its weight drops to ½ pound. Okay? If you have 10 pounds, it drops to 5 pounds. So that's what half-life means. It's just decreased to half the measure of the weight in this amount of years. Somebody measured it this way. Okay? And according to this computation, they came up with a formula that measures the weight, okay, anytime, because you don't have time to wait 138 years to measure half of it. Like, what's the new weight of 1 pound is gonna be in 10 years? You're just wondering how the new weight is after 10 years. You plug in 10 and you compute this exponential function multiplied by 0.3, and then you get the actual weight dropped from the original weight. This is the original weight. You have 0.3 milligram, very little amount of polonium you have, but you're wondering what amount it changes to, for example, 1 year, 2 years, 3 years later. It's gonna be definitely less than 0.3, but how less? Alright, I'm sure it's gonna be more than 0.5. I'm sorry, 0.15, because half-life is 138 years, and we're just waiting several years. So it's gonna be more than 0.15, but that's not the question actually. The question is, they are wondering, what is this? They are wondering the new amount of the material after 138 years, 138.4 years, exact half-life. If you wait exact half-life, how much material will be left if you start with 0.3 milligram. Okay, so we can actually logically answer this question. You're exactly waiting half-life period 138.4 years, and you have started with 0.3. What will be your initial estimate? What do you think is going to happen? Can you guess the answer right away without any computation? Anyone? Okay, that means you didn't understand what half-life means. Again, half-life is, I have an initial substance. Yeah, Chris, you know?
0.15.
Okay, Chris says 0.15. How did he come up with this answer? Look, it's exactly half of the original. Half of the original. Why did he come up with this answer? Because 138.4 is the duration you need to wait to get it exactly half the quantity. Right? It says here, half-life is 148 years. You wait this year, you get half of the initial amount, and they have provided us 0.3 milligram. Okay? Then, if you waited already half-life term, it's gonna drop to half, 1.15. Okay? That's my answer by just reasoning. But if you wanna do the real math, how would you get the same answer from the formula? Formula says A of t is any year, any time you want to measure the leftover amount of polonium in the sample, you just need to insert that value, and I see that number is 138.4. Let's put it in place. What happens if you divide 138 by itself? This turns into 1. Look, you have exactly 0.3 times 1 over 2, half of 0.3, and our answer has been just verified by computation, by the formula. I already knew it, because I have exactly weighted that exact time needed. Okay? So why don't we go ahead and enter this to our first part. Alright, that's 0.15. Wow, why is it wrong? Oh, okay. I'm sorry. I'm wrong. I'm answering the wrong question actually. That's why. My question is a little bit different. It's 0.8 milligram. So in my question, this number is 0.8. If that number is 0.8, then we have 0.4. Okay. Alright, next. The number is 276.8, part B. Now, how did they come up with this number? Why would they pick such a number? Why didn't choose 300? Why didn't choose 200 but 276.8? Do you see a relation between these two? What's the relation between 138 and 276? Chris?
It's 138.4.
Yeah, this is twice the original amount you have waited. It's actually twice half-life. So your material already dropped to half. You are waiting another half-life term. So what do you think? What do you guess your answer will be? This is twice waiting period. You had started with 0.8, drop one period, drop to 0.4. Another period, what value are you going to drop to? 0.2, yeah. But let's verify it. So we start with 0.8, and you plug in 276 over 8 over 138.4, and we know exactly this is 2, and square of 1/2 is 1 over 4, and 4 and 8 cancels to 0.2, and voila, our answer, our guess is right. It's 0.2. Okay, and the last one, okay, this is the weird one. It's 500 right now, and for this you need definitely a calculator. Why? Because it's not a whole multiple of the half-life. 500 is not just 3 times the half-life. So when I enter it here, this division 500 over 138.4, this is not the whole number. So I won't be able to hand calculate this thing. I need help. Or you can just type this into Google or your calculator. It will tell you that it's 0.8 times what? 1 over 2 raised to the power of 500 divided by 138.4. Alright, I already see the answer there, but so they want 3 decimals, round to 3 decimal points. So I'm going to stop here. 0.065. It should be definitely less than this value. Okay? Any questions? Alright, this is a nice application of exponential functions. It's using a brand new formula they have given us, but this is an exponential function. You see 1 over 2b, and the top is changing. Top is t, the time. Actually, have you ever wondered how they come up with, they find an artifact or dinosaur bone, and they guess, okay, this dinosaur lived 100,000 years ago. How did they come up with this number? It's the same procedure. They measure the carbon in the bonds, and they actually do, again, half-life computation. Okay? Alright, 4.2 is over. Exponential functions are done. Any questions? We're gonna start 4.3, which is logarithms, coming up next. Before defining a logarithm, I want you to look at this table, please. What is this function called? What is it called? 5 to the x. What kind of function is it? Polynomial?
Exponential.
It's exponential. Very good. It's an exponential function. So I bet this section is closely related to what we have just learned. Exponential functions and logarithmic functions are somehow related. Let's build that relation. Let's learn how that relation works. Now, there is an equation you need to solve. It's 5 to the x equals 5. Can you guess? Now, just don't look at the right side, please. Can you guess what number you insert in x and 5 to the that power is gonna be 5? What power is that? Very easy question. 1. Of course, 1. What power of 5 makes 25? I'm skipping to this one. 2. What power of 5 makes 125? 3. If I do even the next one, what power of 625 makes what power of 5 makes 625 is 4. Okay, so you're great with certain numbers. If I give you 5, 25, 125, 620, you can find it. However, if I give you 20, can you tell me what x is going to make fifth power of it 20? Can you say, no, there is no solution? Can you say that? I can never find such a number. No, you cannot say that there is a number between 1 and 2. It's going to make 20 because if I put 1, it's 5. If I put 2, it's 25. 20 is between them. So I'm guessing a number between these two. And the graph of 5 to the x is 1 to 1. It's not skipping any values. So there should be a value at 5 to the x. Look, this is the graph of 5 to the x. It's like this. Here is 5 to the 1. Here is 5 to the 2. This is 5. This is 25. And I know 20 is here. So I'm guessing a close value to 2 is going to make it like 1.8. Shall we try? 1.8. Let's try 5 raised to the power 1.8. Let's see. Google, tell us, please. Alright, you're close. You're not 20, but you're close. I need to increase this up. How about 85? Alright, I'm getting there. How about 85, 9? Alright, almost. Oh, I'm really good at this. How about 61? Okay, almost there. How about 65? Oh, I'm too much. So how about 64? So you can do this all day. It's really fun. Can you ever be able to hit this number? Can you exactly be able to ever find this number hitting exactly on the nose 20? Can you ever be able to do that? Answer is no. Don't waste your life. You're young. I know you have a lot of time ahead of you. Don't waste time, more than 10 minutes, because this is gonna be a never-ending number like this. All random numbers keep going and going, and you will still, after 10 years, you will still not be able to get 20 on the nose. So what does this tell you? This tells me that, yes, there is a number. It is 1.8 something blah 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 blah, but it has so many digits, we cannot list digits. We need to come up with a short notation, just like for e and pi, we call it e, we call it pi, those never-ending numbers. We need to come up with a shortcut for this number. What do you want to call it? From now on, I want to call this number 1.8 blah blah, whatever it makes it 20, the special letter A, that's my capital. A, I declare from now this fancy A means whatever that number 5 raised to the x makes 20. Nobody can ever spot it because it's never ending. So I declare it A. This is what actually math people did. Every time they couldn't answer what power that was, they come, for example, this was something between 2 and 3, maybe 2.7, 2.8, let's say, something blah blah blah. They declare it fancy B, for example. Now, eventually, after a while, they ran out of these fancy letters. So they needed to build a standard way to call these numbers, because you use A, B, C, Z, and omega, alpha, all Greek letters. You run out of them eventually. So we need an unlimited notation for it. They come up with log notation. They said, I don't know why they came up with the 3 letters. I'm okay with just L, right? I mean, why did they, I don't know, but they came up with a shortened version of logarithm, because there is some algorithm here. They said, instead of calling this fancy name, I will call you log, three letters instead of 1. But you actually didn't pop up randomly. You are linked to these numbers. So instead of just calling it log, and because these two are the same now, I have to discriminate these. To discriminate this, I need to put you an additional number. They put this base number here. They put that base number here. And the answer, when you raise 5 into that, they put that answer into this. So this could be different. This is log 5 again, 60. This is log 5, 20. Actually, you know what? This can be also turned into log formula. It's just log 5 of 125. Even the whole numbers can be turned into log formula. This is log 5 of what? 5. What is this? Who can turn this into log? This is log what? You put this base to the base, right? And you put the right side afterwards. Again, why did they do this? Just they ran out of these fancy numbers, letters to call them. Pi and E was already taken, okay? So instead they said log 5 and 20. log 5, 125. And some of these log notations are computable. You can perfectly compute them, like 3, 2, but some are not computable. This you cannot compute, okay? Okay? So this is what we're going to be dealing in this section. A lot of these log notations, log notations, and their properties, and compute those who are computable, such as log 5, 125 is computable as 3. How can we, once they give me this, how can I get 3? What's the logic? What's the trick? There are 2 ways you can do that. We will all cover that. But this is extremely important. Now we're making the formal definition. Log notation is nothing but rewritten, reformulated way of turning exponential functions. So this is exponential equations. Exponential equation. Look, I had a thing like this here, right? Exactly. I have an exponential equation like this. I just turned it into log notation. I'll call this x equals log 520. Okay? So don't be fooled by the letters. Forget letters. I actually want you to turn these letters into geometric objects, because some people think, oh, which one was x, which one was y. We don't care what's x, what is y. Think like this. You have a box, triangle, and circle. Just learn how we are rearranging these. To convert this into log notation, I put first log somewhere in the white page, log. The box or the base comes to the here, so this is box. Box goes here. Okay, this is triangle. And I'm going to choose a different color for it. And the circle is purple. Okay, now the triangle goes, where does the triangle go? So you need to first put an equation. Either you can put it to the left or right. Pick a side. Which side you want to put? I want to put to the left side. Okay, now I know where box goes. box or the base of the exponential equation goes here. Just tell me, where does the triangle go? You have two spots. You can put it here, you can put it there. To the left. Yes. Triangle goes away from the logarithm. Again, exponent, this is exponent, this is base. Exponents go outside the logarithm to the opposite side of the logarithm equation with the logarithm. So you have an equation you built. You choose triangle on the opposite side of logarithm. Then you have only one shot left for circle. Circle goes here inside logarithm. It's all about reordering these three geometric objects. Most people think through XYBs. It's confusing with XYB. Forget XYB. Base, exponent, and I call this number or free number. Free number, it's not linked to anybody. It's on the other side sitting free. Free number goes to prison inside logarithm. Base is the guard of the prison. And whoever locked earlier on the tower of exponent, on the exponent of the exponent, is now free on the other side. Okay? Alright, let's try. Let's practice. Who can convert this into exponent form? Okay, in my scheme, this is box, this is triangle, this is the circle. First off, you build your equation here, okay? And you need to put this base into the base of your exponential. So 2, which side you want to put 2? You're free to put 2 anywhere, left or right. To the right, okay. Choose 2 here, that's your box, base, base, base. So base must have a power. Who comes to power? Base almost. Box must always have a power. Who comes to power? 2. Triangle. And the guy locked in logarithm now free without any power or anything. So goes here. 4. Look what we built. 4 equals 2 to the second. Is this a correct statement? Is 4 really 2 square? This is how you check, kinda. If all three things are numbers, you can check whether you're on the right track or not. But if sometimes one of these is a variable, you can never be sure. But this you can be sure because all these are numbers you can verify. Okay? Alright, who wants to convert this? Oh, okay. Maybe for this one I should first mention you this. Sorry. Computer just randomly assigns questions, but it's something you need to know far ahead. If you don't see any base in a logarithm, missing base, right? It's not actually missing, it's hiding from you. You just need to write it explicitly. What is that base? If you don't see it, that base is 10. We skip writing base 10 because it's common. We call it common logarithmic function. So go back once we learn this. So there is a secret base 10 here. Now convert this into exponential expression. Anyone? Any volunteer?
Equals log. Wait, no, I'm thinking log. Equals 10 to the power -4.
Good. Again. Base, new base. Free guy. Oh, we call this triangle, right? Triangle, triangle. And prisoner is free now. It doesn't have any logarithm, doesn't have any power, or it's not in the exponent. It's just on the other side, standing alone. Okay? Alright, next, this one. Anyone? Or you could have built this. 9 to the power 0 is 1. Again, do we always need to put the box to the right side? No, you can start putting box to the right, triangle right above it, and the free guy to the right. You can build an equation like this, then you will have 9 to the 0 equals 1. You can flip the sides, okay? Free. Alright, you've done enough with logarithm to exponential conversion. Now we're doing backwards. There are exponential equations. We're gonna do logarithm backwards. This is box, triangle, free guy. Any volunteer?
Log base 5 power of 125. Or no, log base 5 of 125.
Good. Okay. Again, base. Oh, I put the triangle in the wrong place. No, right place. And this. Alright, I need a new volunteer, not Kylie this time, for this one.
Log base of 1/7 343, and log base 1/7 of 343 equals negative.
Good, thank you. Courtney or Madison? Okay. For this one, any volunteer? Kyle, what do you think?
Log base of P times Q equals 7.
Good. Everything fine, except when you are reading this, we call it log base of POQ, then times, okay? There isn't real multiplication here, it's O. This is inside of this function. Just like f of q, we don't say f times q, this is logarithm O q. You can think of a secret parenthesis though. Alright, so it looks like we are all ready for the next phase. How do you use this fact to evaluate logarithms? And you need to know one simple more fact. Actually, you have already used this. If you have an equation, both sides have exponential expressions with the same base. This is essential. They are the same base, that you can simply wipe off these and get x equal y. Where did you use this? You actually used it here. I said, what power of 5 is 125? And you told me 3. But how did you do it? This is how you actually did it. You turned 125 into power. It is 5 cubed, right? And you did this. Oh, these are the same bases, so tops must match. You kinda, in your mind, drop those 5s, and you ended up with, oh, x is equal to 3. So you're all doing this in your mind quickly. You're not doing this kind of algebra, but this is the underlying fact behind that. If you have same bases on either side, we will wipe them off, and with gravitational force, these guys fall to the ground and become equal. Okay? So, how is this gonna help us here answering this question? I am clueless. These are exponentials, and they're asking me to use this fact in a logarithm question? How on earth can I use exponentials in solving logarithms? Any ideas? I don't even know what this is. So can I call this x? We're looking for x here, right? Unknown. What is this equal to? Unknown. I know you can do this by calculator. Don't use a calculator. I know you may remember some logarithm properties to tell 49 can be done, change it to something and cancel. Don't do that. Just use this fact and this fact. if somebody is asking you a logarithm and you're not allowed to calculate and you don't know logarithm laws, then you must make it, this thing, an exponential. Change this into exponential equation. Can anyone change this? It's Kylie?
7 to the x equals 49.
Yes, it's 7 to the x equals 49. Next, to be able to use, I need to raise both sides to the power of 7. This is already 7. 49 is 7 squared. Wipe off these, and you got it. 2. The answer is 2. Go ahead and do number 7. By the way, do you know how to type in logarithms here? There is a button for logarithm when you need it here, okay? This is 7 though. This is just number answer, so it's easy. Again, don't cheat and use a calculator. You're gonna pay this off, pay the price in the next sections, because you need to get used to do these hand calculations to get ready for the next phase. So don't use a calculator. For verification, yeah. Once you're done with the question and you want to verify you're right, yeah, just use a calculator, but no. Calculators are your enemies in this course, okay? They're great once you learn calculus, once you pass graduate college. Yeah, that's our best friend, calculators, because we already know this stuff. We want to save time, use calculators. But now, when you are a learner, just go with the hard way. You've seen the Karate Kid in 1990s. He was working hard before learning karate moves. He was carrying bottles of water and cutting trees. Just get you ready, okay? Anyways, let's do this one next. So again, call this a variable x, y, z, anything you want. I call it x. And change this into power first. 5 to the x equals 1 over 25. And this one, this is a hard nut. I have no clue how to find x here, unless you guys change that 1 over 25 into power of 5. I know how to change 25 into power of 5. What is it? 5 to the second, right? But now can I wipe this off and say x is 2 or 1 over 2? Does it work? No. To be able to use the property of wiping off, this should be on same powers on the same side, not in the denominator. It should be on the top without a fraction. So you guys need to figure out a way to move this 5 squared to the top. And I bet somebody remembers it. How do you guys move?
Make it negative.
Yeah. If you don't like a power in the denominator, you want to make going to the top, you make that power negative. That's it. Just choose the opposite sign. So here is a rule again. This is the rule. 1 over something raised to the power n is equal to same base with opposite power. For example, what if you had 1 over 2 to the minus 5? This will turn into, if it's already negative, what do I do if it's already negative? It's gonna be 2 to the positive 5. 32. 1 over 2 to the negative 5 was actually a 2, 5 times 2 itself. It's 32. Okay? So if you already have negative power in the denominator, it turns into whole number. Alright, anyhow, we got this now. It's 5 to the x is 5 to the second, negative 2. This gives us x equals negative 2 once you wipe this off. Okay? Alright, let's take a look at the next question. Now it's time to learn two famous logarithms, two famous ones. First one is called common. If you have a base 10, we don't literally show it all the time, so we skip writing it. And when you see a logarithm with no base, just as default, that base is 10. It's called common logarithm. The second one is called natural log. It's the one with base e. E is called natural number, 2.7, blah, blah, blah. But when you see that 2.7 under the logarithm, here, we turn that four letter, L-O-G-E, 4 letters, instead of 4 letters, we just call it ln, 2 letters. ln means log base e. Okay? Any questions? So when you see ln, that means log base e, and then you have whatever following it. This means again log e of 1 over e to the 7. And this means log e. Am I right? No, it's not log e. It's log what? 10. If you don't see a base here, no base, that means it's 10. Log base 10 of 0.0000, I don't know how many zeros, 6. Okay, so these are the questions we are trying to answer, so I will set them into x. And you need to find out x's. Okay, I know I can't do it by hand. I can't guess it right now. So we need to change this into exponential. Let's change. Any volunteer? How do you change this? Ashley?
It's just 5.
No, you're telling me the answer. I mean, just change this into exponential. Again, this is your box. This is circle. This is the triangle. So box goes, you put box anywhere, right or left. And then, so it's E, right? And then triangle goes around the box, which is X. And the stuff under the logarithm goes to the other side as free. E to the 5. Purple, green, red. Just reordered. Now, what happened here? E to the x equals e to the 5. Can we employ that same rule? They said if the bases match, x is 5. You're right. Okay? Make sense? We will learn how to do this faster in a moment, but right now this is how we do this so far. Here, change this. Box, prisoner, triangle.
E to the power of x equals 1 over e to the 7.
Yep, e to the power of x equals 1 over e to the 7. We have the same situation. This is just non-fraction numerator whole thing. This is 1 over e to the 7. E to the 7 is in the denominator. I cannot wipe these off. So what do? We change this into e to the -7. Okay, and clear these out. X is -7. Okay, and this one is maybe most tedious one, tricky a little bit. Any volunteer to change this? Mm-hmm. 1, 2, 3, 4, 5, 6 zeros. Let me double check again. 1, 2, 4, 5, 6. Okay. Alright. Now, how can I? We need to make this into power of 10. How? What power of 10 is that thing? Or maybe we should make that one is first a fraction. Isn't this number 1 over 1 million? Is it? I'm not sure. Divide 1 million, you get 6 zeros. Right? Now 1 million has how many zeros? 6. It's 1 over 10 to the 6. This is 10 million, correct? Should be 10 million. So this has 7 zeros. It's 10 to the 7. Just multiply 7 times, you will see it's 10 million. And I need to bring this up. Is 10 to the x is 10 to the -7. Finally, same result. X is -7. I'll make sure this one is right. Number 12. Yep. Any questions? Make sense? You just need to change numbers to powers and set them equal. That's it. Alright, as you've seen, some of those easy questions can be pretty challenging, like converting into zeros to the powers and 1 over e to the 7. I wish we had faster tricks that can take our solutions shorter and faster, and we can get to the result faster. And somebody did it for us. They have experienced that when they did over and over these computations, some of the logarithms always gives the same answer, such as they try to compute logarithm of any base of 1, because you need to change this into exponent and it becomes b to the 0. Any number raised to the 0 is 1. So any logarithm of any base of 1, if you see the magic number 1 inside, it's 0. So from now on, when you see 1 in a logarithm, the answer is 0. Please do know these 4 properties. They make our calculations a lot faster, more efficient. Okay, if you have these two numbers matching, the answer is always 1, no matter what b you take. B is 10, b is e, b is 100, b is 1 over 2, even rationals. If you see these are matching, it's 1. So this is property of 1. If you see 1, it's 0. This is property of matching number and base, matching number and base. This is property of matching number and base, but the number is raised into another power. I call this power rule. Okay, So you have a power, but these two are matching. This is important. These two are matching. You can't do this with any other number. If this is C and that's B, we cannot say the answer is X. They kinda cancel these two out and get X as the result. Why is it happening? Because b to the x is exponential, logarithm is inverse of exponential functions. Exponential function and logarithm cancels each other. These cancel and you get x. Same thing true if logarithm goes to the exponent of a base. They cancel and they turn into x. Again, when do they cancel? This is kind of tiny to see for you guys, but these bases must match. If they are matching, then we can cancel. Make sense? Alright, please, I want to add a fifth property here. Please write this down as well. What if you have a logarithm b c to the x? Again, logarithm with base b, but you have an exponential, but that has c as a base and x as a power. Do you know the trick with this one? Can I cancel these and say it's x? Can I? No, because b and c are different. I can't cancel. There is one thing you can do. Do you know? Does anyone know what you can do? You can kind of simplify this a bit. It's not gonna be a whole number as this in the previous ones. You just rewrite this in a simpler way, different way, which is no. You can take this x to in front as a product, so it turns into x times logarithm b of c. So that actually explains how number 3 happened. Look, anytime you see a power, this power can be brought outside in front. So I will do that x. And what is a logarithm of matching numbers b and b? Logarithm base b of b. It's by rule number 2, it's 1. It's x. That's this rule I gave you, number 5, actually covers this. You can get this. Look, I got it. Logarithm bb of x, bbx is just x. I have proven it by using 5 and 2. Okay? So I like this one. It's coming handy. So keep this in your list as well. This is I call power law, general power law. This is specific power law because you need to have b's matching and x exposes. Here we have more general case because we don't push b and c to be equal. They can be different. Then you only bring x out. If c becomes equal to b, then yeah, they drop out and become x only, but it's not the case here. Alright, let's do next 3 questions very fast because these are no-brainer. You don't have to do computation. Again, you do not have to change this into exponent. You don't have to change exponent. You can now answer these by using one of the rules in the list. Which one? Which one do you think we're gonna use? It's 3. It's matching pairs with a power in the inside. So this is simply kind of cancel these and become 5. How about this one? This is easy. What is logarithm of dd? I don't know what d is. I don't care. It's 1. It's rule number 2. Rule 2. This is rule 3. What rule is this? Rule 1. How come? Whenever you see 1, no matter what the base, I don't even look at the base. If I see 1, the answer is 0. 1 is a logarithm butcher. It just cancels it and makes it 0. Alright, okay, this one is kinda interesting. I see a ln and I don't see a base. So what does ln mean again? It's a logarithm. What kind?
Yeah.
Natural logarithm, but what base? It's e. There is a secret e there. You have another e coming up, and you have r squared plus 3 on the exponent. I want to put this in parentheses just to let you see they are both on the exponent. Okay? Now what can I do? By rule number 3, rule 3, if these are matching, these two, I can cancel them. What is the result then? The result is this whole parentheses, this thing, r squared plus 3. Okay? It's 16. Alright, we have a couple more left. They are about graphs and domains of logarithmic functions. And there's gonna be one application afterwards. Earthquake measures or scales are actually developed from using logarithms. Okay, so before that though, we need to get to know graphs of logarithmic functions. Okay, logarithmic functions are built from exponential functions. They are inverses of logarithmic exponential functions. In the previous section, we have just learned about this. This is section 4.2. I've told you that exponential function goes up, or we call it growth, if b is more than 1. It's decay if b is less than 1. Now, when we started this section, I told you that inverse functions have graphs. Okay, complete the sentence. What kind of relation do you have between a function and its inverse? So I'm assuming you don't know this. Only I given you this. How would you find inverse of this? Or logarithm is the inverse exponential. How would you find its graph? (4.1) inverse of a function. Uh, 4.1. Anyone knows? Yeah, we switched x and y's. How? Technically, through with the help of what? It's right here on this example. How did they find this orange graph from the blue one? Orange is the inverse of blue. They switched x and y, right? But they did it over using this line, y equal x. They flipped it over. They took symmetry of blue according to the black dashed line y equal x. We're gonna do the same thing. We will put a dashed line here and take symmetry of this blue for this growth one. Take symmetry, and what do you get? I get this. It's too close. Okay, this point is gonna be here. Alright. This point is gonna be here. This point is gonna be here. And this point is gonna be here. So it's gonna be something like this. And it's right here. Isn't it the same when I put this dashed line here? Okay. When you flip the decay one, you get this one. Alright? Alright? So, there are two shapes for logarithmic functions. Either growing, again this is growth. This time growth is this. B is more than 1, you have growth. And decay one, or going down, I don't want to call it growth because this is increasing. This is increasing 1. This is decreasing 1. Decreasing 1 is when B is less than 1. Okay? And what is one thing common in every logarithmic function? They always cross this point. Why? Because no matter what base I take, what is logarithm of b of 1 if you enter x equal 1? This is x equal 1. If I enter 1 into x, what is logarithm of any base of 1? It's always 0. That's why they meet no matter how different b is. They always meet here, just like exponential functions meeting here. Okay? Alright, here are more properties. Domain of, extremely important. Please put it down. Domain of any logarithmic function must be positive. X should be positive. You cannot compute logarithm of 5 of negative 3, undefined. This should be positive, not even 0. Can I put 0 here? No. You see, these curves are not touching x equals 0 line or y-axis because you cannot enter 0 and compute it. It's getting close but not touching them. So they have a vertical asymptote. X equals 0 cannot be touched, but you get close, it's vertical asymptote. Range of logarithmic functions is all numbers though. Look, it's going all the way up and down. So this is the range. Entire y line, y-axis is the range. Because they go all the way down to up, they go all the way up to down. In either scenario, you cover all y values. So range is everything. It passes through 1, 0. If b is big, it's increasing. If b is small enough, the function is decreasing. We already mentioned it. Increase. And this is summary from last section, again, section 4.2. We already seen this there. It's just comparing. You see, it got opposite because they are inverse of each other. It used to be y equals 0 horizontal line. This is vertical asymptote. Instead of horizontal, vertical, opposite situation. 0, 1 got opposite, 1, 0. It was increasing. Now this is the same though. This part stayed the same. Okay, now once we know this, you can sketch this, guys. How? You need to start somewhere. You need to start with, this is the main function. Sketch logarithm base 3 first. Then you can figure out this one and that. These two are transformations. Once you sketch logarithm 3x, you're gonna transform this by adding 3 to x's. This is one transformation. This is another one. You need to name me these transformations. What does adding 3 to logarithm 3x will do? Adding a number. Ashley? Yes, this is left 3 because it's only happening to x's. It's not to the end. It's changing x values directly. So what kind of shift is this? Down 1. Okay, just sketch logarithm 3x first, then do these two effects. Okay. This one. Okay, to sketch logarithm 3x, if you don't know its graph, I have an idea. Logarithm 3, base 3, base is 3, it's more than 1, it's gonna be looking like this. So my rough estimate is, yeah, I'm expecting something like this, but I need to make a precise picture. So why don't we set several values to this? X log 3x is y values. So what kind of numbers you want to test? For example, I want to take 1 because I know logarithm 3 of 1 without a calculator. What is logarithm 3 of 1? It's 0. So I know this is 1, 0 already on it. It's as default on every logarithm. Okay, which number you want to take next? Don't tell me 2. Why? Why is 2 bad? Can you compute logarithm 3 2? By hand? No. So instead, what number would you take? 3 makes sense because what is logarithm base and number matching? If they match, if they become 1, 3, 1, 1, 2, 3, 3 and 1. Okay, so I need to revise it. You see it's not crossing here. Take this away, take that away. Second one is 3, 1 here, guys. Okay, give me one more. Something before 1, 0. I need, what do you want to put? How about 1/3? Why did I choose 1/3? What is, let me do it here. What is logarithm of base 3 of 1/3? Isn't 1/3, this is first power, 3 to the negative 1, right? I choose 1/3 so I can raise it to a negative exponent of 3, and these two cancel. The answer is negative 1. This thing is negative 1. So 1/3, I know where is 1/3. This is 1/3. It's just 1/3 out of this length makes negative 1. Where is negative 1? It's somewhere here. So the point is there. And if you need more and more dots, you can get more and more. I recommend doing 1/9 if you wish. And I recommend doing 9 because 9 is a square of 3. 1/9 is 3 to the minus 2. They all can be computed. This thing is minus 2. You get down. Alright, I can't do it. 9 is out of my range, but it's somewhere up here. Anyways, this is the plot of log 3. But I need it left 3. I need to move it left 3. This is gonna go 0, negative 1, negative 2. This point is gonna travel here. This point is gonna travel here. This point is gonna travel to here exactly on the y-axis because this is 3 units already. This point is gonna move here. So this is left 3, but I need it down 1. So when I bring this down 1, it's gonna go here, and this is gonna go here, and this is gonna go there. Something like this. Okay, now we're almost there. I'm sorry, I'm 1 minute ahead of time. But you need to write domain and range in interval notation and equation of the asymptote. I will continue the rest tomorrow. We did the graph. Well, we need to read a couple of info from the picture and the equation as well.